Okay, so I think I'm here, and so we start. So everyone, welcome to our session of urban planning, construction, and disaster management. I'm Simin Chen from Fudan University. So today I'm happy to chair this session and welcome our 6 speakers here. So let's start the first one from Saeed Boorboor. And his talk is Submerse, Visualizing Storm Surge Flooding Simulation in Immersive Display
Um,
Ecologies. So welcome. Uh, is okay? Everything okay?
Hi, yes, thank you. Thank you for the introduction. And I'm Saeed Boorboor, and I'll be speaking about Submerse, which is an immersive visualization system we have developed for storm surge simulations. And for this community specifically, flooding and disasters was not a surprise, as we saw just in the span of 2 to 3 weeks, we had 2 intense hurricanes. And speaking about that, floods are actually the most frequent form of natural disaster.
Hi, sorry, I have to interrupt you. Do you have audio on?
Yes, I do. No,
I think I can hear his voice.
you can hear me?
Everything good? So is there any problem with the YouTube? So probably technician will check the
Yeah,
YouTube.
so you need to turn the YouTube feed off because there's an audio feedback loop happening otherwise.
Who is opening the YouTube here?
No, I think it's okay now. Thank you.
Okay, so
Okay.
you can continue.
Okay. So I guess I'll speed through my slides now a little bit. Sorry about the technical difficulties. So what happens is in preparing for these events, for impact decision making, it has to happen on different timescales. So, for example, National Weather Services needs to communicate these hazards to stakeholders on short notices, like 1 to 4 day timescales. Again, something that we just experienced weeks ago when we were planning VIS. Then there's also this layer of communication to communicate impacts and hazards to the general public through infographics or journalism. And typically, what happens is these geographically based predictions, especially for flooding, are visualized as low resolution layers of digital information that is superimposed onto things like map or map like features. And with limited screen display and with such a platform, what happens is we are constrained to a lot of pan and zoom interactions. So we lose context of surrounding areas or larger field of view. There have been works to extend these visualizations to 3D. As we know, 3D can enhance the user's understanding of, let's say, depth and its impact, its intensity with respect to its spatial surroundings. Again, also, we've seen more and more journalism media moving towards these 3D visualization to create sort of an impact within viewers. It's a fine line for not to create panic, but also to have preparations at hand. Extending it further, specifically for scientific analysis, large high-resolution displays such as power walls, caves, and immersive tile display facilities have now more and more been shown to improve user performance in various visualization and analysis tasks. In essence, utilizing this large screen real estate allows for a wider field of view, particularly beneficial for applications such as flooding visualizations, where you have immediate access to local data by just walking close to the screens, but then also global data or context as you walk back and look around. And this is very vital for well-rounded analysis and decision making. Moreover, with these facilities, we can really utilize the computational and high-resolution display graphics powers. And this idea of using multi-display systems or increasing our screen real estate is not an uncommon phenomenon, especially in emergency management departments. There's this whole overarching view using lots of LCDs or screens, but then at your local context, you have desks and workstations where experts from different various fields are working at more localized contexts. So inspired by all these, we've developed Submerse, which is an application and a system for flood visualization that harnesses the screen real estate for large display facilities and really clocks on their visual activity. We address three important designs, which is visualizing simulation data, coupled with elements of geographic information systems, maps, and auxiliary data. Then we have an AR-based data interaction modality, and also feature for tracking camera movements, which I will speak about. So the first task is we want to render the simulation data, which serves as input to our application. Now, typically, simulation data are in the form of the scalar water elevation values, sometimes additionally with 2D velocity for these values, but they're arranged on an irregular grid because of the sensing and the way the data is distributed. So the first task is we want this high-resolution grid desirable for generating a smooth mesh of continuous water surface. Now, this could be high in memory and performance if these simulations, because they run over a wide range of area, to kind of render them for the whole spatial extent, especially for large display facilities where the field of view is much larger. So for enabling a high-performance throughput, we adopt adaptive height field, which is discretized representation of data. This has been previously presented by Cornell et al., and so we developed that on top of that to have a sense of dynamic quad-tree data structure that supports, specifically for immersive displays, a level of detail rendering. So to kind of brush over its features, the elevations are discretized on this quad-tree, and the value of the heights are cell-centered. And each parent resolution is a definition of the level of detail, which is an average of its higher levels of details. And if you compare our simulation data, as you see, they're on an irregular grid, so there are these areas of missing information. So to kind of fill those up, we use average data from the nodes around it. And now I'll briefly give you some features of how data is interpolated as we are rendering any level of detail mesh. So for any point on the quad tree, based on its level of detail, its value sampled using its neighboring nodes. Now, if you notice here, what's happening is we have equal levels of detail for 3 of its neighbors, but missing for 1 neighbor. So this is what we call the unknown sampling point, which at runtime we can upscale, because as you can see, it's on a lower level of detail. So we want its higher level of detail resolution. A similar process is adopted where we can now interpolate it based on its neighboring level of details. Now, if you notice here, one of its the neighbors have a higher resolution, higher level of detail, and for that we basically do downsampling, which is an average of the child nodes. So now that we have all neighboring cells and its values, a value is interpolated using bilinear interpolation. As you can see now, given simulation data, we have this smooth water interpolation across each node on any level of detail grid that you want. And the fact that it's dynamic is we want to maintain interactive frame rates for exploration. And so we track the virtual camera that moves across the scene. And based on the buffer zone, we can update the appropriate quadrant in the quad tree instead of reconstructing and repopulating the values for an entire quad tree. Now, as you know, for things like floods and for behavior of flow, like inundation, information cannot be perceived by just observing a static mesh, and we need some kind of a flow. So in our simulation data, we also had 2D tidal velocity. Now we can use particle systems to mimic flow, but then that would be very high computation again. So we use Gerstner waves to kind of have this realistic looking waves that follow the sinusoidal pattern of displacement. Similar to our interpolation data, wave is sampled across regions, so looking at a finer level of detail to a lower level of detail. And this gives a sense of local as well as regional principal flow across them. I'm not sure of the YouTube quality, but I hope you're able to see all these waves in the video. And then based on the camera's movement close to the water surface, there's also this hardware level mesh tessellation. So now, especially in large immersive facilities, effective navigation is an essential element. And one of the challenges is when you're immersed in this whole room, how do you navigate and how do you effectively go through the entire scene, make sure that all points of interest are viewed? So for that, we have this automatic camera view and navigation path generation based on points of interest that are pre-input by the experts, for instance. So I have this building of interest. I want to have it best visualized in my immersive facilities. We have created this energy function that generates an optimal camera view for each point of interest based on 3 factors that we've determined: view coverage, which is the combination of eccentricity of the point of interest projection on the camera view and its alignment between the camera and the user. Then we want to check if the point of interest is occluded by any other building or object or cell that is maybe taken up within the view. And then this is specifically based on our domain expert requirements that most of the points of interest they want to visualize are on the coastline. It is preferred that the camera view is in direction that is from shore to the point of interest for effectively visualizing the progression of coastal flood. And then finally, what we've developed is also then optimizing this view best for any kind of display facilities. You have a 4-wall, you have a 3-wall, you have a single screen. So these camera views are also take into consideration what is your perfect combination. As you can see here, so if you have a single screen, and these are the points of interest in red that you've marked, you'll have several more kind of views that you would want, and then there's a trajectory that we generate using Bezier curves of these views. Whereas if you have a 4-wall tile display facility, which in our case is the reality deck, Stony Brook, that I'll talk about later, we have these couple of views that we can seamlessly create this navigation path across the whole downtown Manhattan map that is seen here. And because we have this dynamic quad tree and we have this pre-computed camera views and paths, now we can also make sure that the data is populated and rendered in more effective and high performance metric. Now, again, thinking of interaction with data, for flooding and for visualizing such intricate data, there is a lot of local and global context. Now, unlike desktop applications, we really don't have a graphical user interface. You don't have a keyboard and mouse to open GUIs and stuff like that. Typically, you do walking and hand gestures. Occasionally, we also have handheld controllers. We want an additional layer of visualization, which we have in Submerse implied using see-through AR device, which we call as an auxiliary display into the immersive setup. Essentially, for us, it's a hop of realities. It's augmenting in virtual information on a real world backdrop, which is just flat screens, that is displaying a virtual world. So how do we really utilize AR for that? So we use AR technologies to localize yourself in the physical space. And then based on your interaction modality, and because we have in tile displays some server client architecture, we can extrapolate your physical localization into virtual localization using this correspondence. And then based on wherever your viewport is, we can render this additional information as a texture, which is then mapped onto the auxiliary device. So now essentially, you're using...
yeah.
No, sorry.
So you can continue, but in a very fast way. Thank you.
Right. So yeah, we use this AR displays for things like occlusion removal. You want to see a building, but it's occluded by others. You want to measure the depth, or you want to have other GIS overlays on it. So to kind of wrap it up, the kind of data interactions that we have is you could either walk and pan naturally, or you could use this auxiliary information for more fine-grained visualization for your local kind of visualization. I will skip through the case study, which we did for New York City for a simulation like Sandy. I guess one of the key features was they could have collaboration, and with auxiliary information on top of it, it really transformed the way they did emergency management and resiliency measures. Thank you for that.
Yeah, thank you very much, Saeed. It's a quite interesting work. And because we run out of time, so probably I have a very quick question here. So because you didn't show the case, did you have these interactive features in this simulation that, or how can the decision makers using the simulation that can they see the real changes of different parameters and see the results there?
So in this current scenario, the only change of parameters that they were allowed to do because of this workshop was worst case. So you want 1 meter sea level rise in addition to the simulated storm, or best case, let's say the path. So flooding levels were the only parameter tuning that were allowed at this point.
Yeah, okay, thank you. Okay, so let's come to the second speech from Andreas. And his talk is about the BEMTrace visualization-driven approach for deriving building energy models from BIM. Let's welcome. Andreas, you can open your sound, voice. And your video probably.
I'm so sorry. I'm struggling with my video.
And now we can hear your voice.
That's a good start. Now you can see
Okay.
me as well. I hope so.
Yeah.
All right. Sorry for the struggles in advance. Okay. Thank you for the kind introduction and welcome to BEMTrace, an approach which enhances the data curation process from a BIM to a BEM model by providing the support of the conversion process. First, let me introduce the main not so common acronyms. So Building Information Modeling, short BIM, is transformation the construction industry by integrating all aspects of the planning and building process into a single digital environment. Emerged from 2D CAD drawings, where collaboration was limited to share paper notes, BIM supports detailed 3D representations of projects that incorporate not only physical dimensions, but also metadata such as material properties or cost. By providing tailored BIM views for each involved actor, collaborations between different disciplines are possible without losing track of changes. This digitalization allows for more accurate planning, improved decision-making throughout the life cycle of a construction project from design to completion. Building energy modeling, short BEM, involves creating the representation of a building's physical and operational characteristics. BEM enables thermal simulations to assess and optimize energy use in heating, cooling, lighting, and other systems. It helps architects, engineers, and energy professionals to make informed decisions about building design and energy systems. This allows for more sustainable buildings, reducing energy and operational cost while improving comfort. The conversion process between these two models is called BIM to BEM. Open exchange formats such as the Industry Foundation classes, short IFC, enable the data transfer between BIM tools and could serve as input for BEM tools, but still lack full certification, which could result in lost details on the way. In a BIM to a BEM conversion transforms the geometry of BIM into a suitable form for energy calculation in BEM. In BIM, a room, as you know it, is represented by a space. A space has a certain volume and location. During the transformation, we must find out which other spaces are connected to it. Connections can either be walls, doors, or other building elements. This sounds like a trivial operation, but unfortunately, it is not like that. The BIM to BEM transformation is a tedious and error-prone process because there are no pre-checks in the BIM to ensure that all necessary information for BEM are available. You have to imagine that the BIM is created and edited by humans and transformed several times in the planning process, which introduces geometry conflicts in the model. This includes inconsistencies such as duplicates or overlapping objects, or even missing data in the BIM. Simple heuristics to solve such conflicts fail, because certain decisions can only be resolved by domain knowledge. Here you can see a 3D BEM model, which was created by a BIM to BEM conversion. The conversion was not able to automatically create connections between the room in red and other rooms due to overlapping geometry. Therefore, the need for user interventions are necessary here to resolve this conflict. And this is where our visual analytics solution comes into play, to provide insight and help experts to understand and resolve such conflicts. To help users to trace conflicts back to their origin, we developed the BEMTrace approach. The key novelty of our workflow is the ability for users to interactively switch between all views of the transformation process, while the interface adapts to each view. This consistency is achieved through context-adaptive selections, which combines the idea of context-aware selections, which allows users to only select objects that are assigned to a certain context, and adaptive rendering, which which adjusts the 3D rendering to the current visible dataset. If the user selects a building element in one of the views, we store the information about the selected element. In each view, only relevant information of the current selected BEM objects are shown, while other objects are rendered as a transparent silhouette. Each view depicts a typical stage. By selecting an element in the BEM view, all objects involved in its transformation process are set in focus in each stage of the conversion process. Now I will give you a brief overview of the BEMTrace stages. The BEM view shows the derived energy model, which later serves as input for various thermal calculations. Starting from the BEM view, the transformation data and raw data can be explored. The BIM view shows the unmodified input data from a BIM creation tool. The space view visualizes only volumetric objects, such as spaces and the space category. We use a color coding to identify internal spaces in green, air spaces in blue, and earth spaces in orange. The element view depicts building elements, such as walls, slabs, doors, and windows. The elements are grouped by their material properties, such as material layers and their compositions, which is also visually supported by a color encoding. The relationship view shows the surfaces between elements and spaces, so-called space boundaries. Surfaces originating from the same element are critical for establishing connections between spaces and emphasized by a shared color. So let's go back to our example with the conflict in the upper right room. First, we select the unresolved conflict in the relationship view. By switching to views, we can check the involved objects. The element view shows only one window, while the space view depicts one internal and two external spaces. This is uncommon because a window cannot be subdivided. With that in mind, we go back to the relationship view. By selecting one option in the conflict panel, the related space boundaries are highlighted in the viewport. We can see that the two options overlap on the window surface, which would lead to an incorrect thermal flow. Both options are for themselves technically valid, but recall on the discussion of a later dismissed balcony in the lower section. With that in mind, we choose the upper option to resolve this conflict with our domain knowledge. After resolving the detected conflict in the transformation process, the BEM is now ready for thermal simulations. To test BEMTrace regarding its abilities, strengths, and weaknesses, we combined 4 established evaluation methods to get broad feedback from 7 test users. For the heuristic evaluation, we rely on Walch et al.'s questionnaire where participants rated 21 statements on a 7-point Likert scale. Overall, we received very positive feedback from the test users. Thank you for your attention, and more information are found in the paper, and I'm also around for discussion virtually.
Thank you, George. And yeah, you saved some time for us, so we have some questions. I'll check the Discord, and our audience can present your questions in any form that we provide. So we will report to the authors. And then first, I would like to have my question for my own. So quite interesting work, and I'm thinking, so did you collaborate with some domain experts to do this, or who is your target users?
Yeah, that's a project where our partners are from the building and building physicists, and they were interested into get a digital, automatic digital representation of a building that so they can start to calculate various energy simulations.
Yeah, I'm wondering that. So what's their previous or originally pipeline? So compared with this BEM to BEM conversion you provide. So what's their original pipeline? They also did they also do these kind of separated steps, or So what's the difference so that your approach that help them?
So currently, the project partners do have specialized programs where they have to manually input various data like the dimensions of the connecting areas and so on. So this is quite tedious for those, and the digitalization process is not really evolved that deeply. That's what we try to bridge it with our tool. And one of the thing is that most there are other solutions currently available for BIM to BEM, but the decisions made in the background are not usually easy to understand if there, for example, errors occur. So the trust of the users were not really so given. So that's why we decide to showcase where the stages and decisions have been made from the heuristics, for example.
Yeah, I think it's quite important and useful for them. Okay, thank you, Andreas, and thanks for your presentation.
Thank you so much for having me.
Enjoy Florida. And now we come to our third speaker, Yutian Zhang, and his talk is about the MARLens, understanding multi-agent reinforcement learning for traffic signal control via visual analytics. Welcome.
Hello, can everybody see my screen? Is everything okay?
Yes, good.
Okay, so let's get started. Thanks for the introduction. I'm Yutian Zhang from Xiaxing University. Here I'm to introduce our work, MARLens, Understanding Multi-Agent Reinforcement Learning for Traffic Signal Control via Visual Analytics. This is a joint work by Xiaxing University and Shanghai Tech University. Traffic signal control plays an important role in smart cities, which can significantly reduce traffic congestion as well as traffic conflict. Nowadays, traffic signal control based on reinforcement learning is a leading trend for traffic researchers. Each intersection is an agent. It observes current traffic conditions and decide whether to change the traffic signal phase. The environment will give a feedback to the agent to help it learn policies. Reinforcement learning allowed the traffic signal control model to learn from trial and error and dynamically adjust to real-time traffic conditions. However, high trial and error cost in the real world and interpretability issues still hinder applications of the models. So to improve the interpretability of error-based traffic signal control, we need to address three main challenges, including providing a more comprehensive evaluation of the model, unveiling the dynamic relationships among different agents, and interpreting complex decision-making process of the model. For the evaluation of the model, current researchers, they mainly focus on improving the performance of the model and mainly use some global metrics to evaluate, which may lead to insufficient evaluation. So the analysis of the interpretability has also been overlooked. So in this case, it is of great importance to present a more comprehensive evaluation and enhance the interpretability of the model. For the interpretability of reinforcement learning, researchers often use video games as well as the robot control scenarios. Secondly, for existing some visual analytic systems, most of them focus on single agent reinforcement learning. Also, they cannot provide an detailed analysis of the decision-making process of the model, and they do not support customized scenarios. However, on the other side, for traffic signal control, it may encounter multiple agent settings and need to customize the research scenarios sometimes. And to the best of our knowledge, only a few studies aim to improve the interpretability of error-based traffic signal control models. For the traffic researchers, well, they tend to use domain knowledge to understand and evaluate the model, such as to exploring the relationship between the traffic conditions and traffic signals. Some classical diagrams are also widely used. However, these research do not support multi-level analysis and need for more efficient visualization and interaction support. So in summary, our approach combines a customizable environment for traffic signal control XAI algorithm, and domain knowledge. And then we design and propose a visual analytics system to enhance the interpretability of IR-based traffic signal control for researchers. In the back-end engine of our system, we utilize 3 popular traffic simulation platforms for IR-based traffic signal control to provide a customizable environment for our users. And next, for the understanding of the model, we use SHAP algorithm to calculate the future importance of the model. Also, we record each agent's states and actions, then train decision trees to reflect the decision-making process of the model. As an explainable model, every time we input the states, and we can get a decision path, including all the features that are considered during the decision-making process. This slide summarizes the system requirements. We consider different time granularities to better support the analytical tasks at different levels. And we also enable users to use the traffic simulation platform to replay the training and testing process. Our system consists of several modules. The control panel represents training information related to the model. And the training distribution offers an overview of the model training process, which showcases the distribution of various metrics and allow users to sort episodes by different metrics. User can utilize the training distribution to select a specific episode to explore. After selecting an episode, users can facilitate the exploration of traffic conditions and agents' policies in the episode overview. It contains a projection of the traffic congestion of the road network based on traffic volume. We allow users to select a time period, and then a road network will be updated to display the traffic condition and agents' policies. The size of the sectors indicates the probabilities to turn on green light in the corresponding directions. We design these interactions to summarize agents' policies, which assist users to explore how agents react to different traffic conditions. The episode detail provides a visual summary for each agent and demonstrates the influence and relationship among multiple agents. We use TSNE algorithm to project states into a 2D plane. And this approach ensures that similar streets are closer to each other. When users zoom in, and each state will turn into a glyph, which demonstrate key information about the corresponding intersections, such as number of vehicles at different directions and the traffic signal phases. Additionally, we list top-ranked features outside the ring. A trail diagram is also utilized to display an overview of the influence among different agents. On the right of the episode detail, we have modified a wild use diagram to better demonstrate how traffic signal change over time. The traffic signal phases are encoded by different colors and icons along the x-axis. Also, the use of the line charts can illustrate how the metrics change over time. The policy expanders used to analyze the decision-making process of the model. We have applied a tree-based design to display the decision-making process for each agent at a specific time step. The model uses global and local information to make actions, and 2 branches indicate the decision-making process of the model, including all the important features and final decisions. The value of corresponding features is demonstrated as a red bar within the feature range. We have incorporated a traffic simulation module to replay the traffic condition and agents' actions directly. Users are free to replay the whole episode, select a time step to replay, and adjust the play speed. The module also allows users to zoom in to check more details. Now we use a case study to show how MARLens works. Users initially use the training distributions to analyze global metrics. They try to sort different episodes by time and reward. Obviously, according to the length of the bars, it's obvious that the later episodes shows higher reward, which suggests that the performance of the model has been improved after training. Then the users utilize the policy overview and the episode details and simulation replay to compare the model performances across different episodes. For example, it selects the period of time in the policy overview to explore agents' actions towards different traffic conditions. The size of the sector encodes the probability to turn on green light in direct directions. And the last episode shows a much higher probability to turn on green light in the direction of the main traffic flow. Conversely, the probability is almost the same in the first episode. This phenomena is more obvious in the episode details and simulation replay. According to the color of the bands, you can see that the last episode has 4 clear policies based on different traffic conditions. And the first episode, it can only randomly take actions and cause serious traffic congestion. Also, the user explored the states and actions in the last episode with more details. After selecting a time period, energy states were projected into 2 clusters. For example, according to the size of the pink sectors, it indicates that there are more vehicles in the north-south directions. The agent shows that the agents also choose to allow vehicles in the north-south directions to pass the intersection. So all this above concludes that the agents allow vehicles in the main traffic flow directions to pass, which is benefit to reduce traffic congestion. Moreover, during the explorations, the user found some abnormal vehicles, which appear abnormally in the unexpected directions and got stuck in the intersection. Then the user selected a time step to further explore the decision-making process. And he found that agents also noticed there are no vehicles in the west-east directions, and there are some vehicles approaching from the north. So the agents was inclined to allow vehicles in the north-south directions to pass the intersection. However, the vehicles in the road A1, B1 was ignored, and that's the reason why those vehicles got stuck. So MARLens has a good effectiveness for identifying abnormal situations and explain why the model made a decision in a given state. And experts also provide us many precious feedback. Our systems provides multi-level analysis and enhance the interpretability of the model. They also suggest us to provide more customizable options in the future and so on. We also conduct a user study with 10 participants. Generally, we receive some possible feedbacks and gain valuable suggestions from them. We have discussed how MARLens improve the current workflow of domain experts, how to effectively communicate with domain experts, and the real-world deployment of our system. So for limitations, our systems now is unable to handle extreme large road networks. A more comprehensive user study can also be improved. And in the future, we will consider more end users and provide a more diverse, customizable options. So that's the end of it. Welcome, refer to our papers for more details. Thanks.
And thanks very much, Yutian. And it's quite interesting work. Let me check this Discord and not yet. So I have a question. Would you come to your case part? So I'm not sure because now you only model like the one agent here, or at the same time there are multiple agents?
Due to the time limits, actually we conduct some analysis of the interaction among multiple agents, just as we find that there is one intersections, and also the surrounding intersections will have a strong influence on the on these intersections. So there is also some findings, but due to the time limits, I cannot explain all the details about our cases.
Yeah, it's okay. So yeah, but I think it's quite interesting work that combine the reinforcement learning with this visual analytics in this traffic analysis area. Okay, so our time is also yeah, and thank you.
Oh, thank you.
So we can have our next speaker, Juntong Chen, and his talk is about a sense map, urban performance visualization and analytics with via semantic textual similarity. Let's welcome.
Hi, can you see my screen?
Yes.
Okay, thanks. Good morning, everyone. So I'm happy to share my latest work that published on TVCG this year, Sense Map, Urban Performance Visualization and Analytics via Semantic Textual Similarity. Nowadays, more than half of the world's population resides in urban areas, and their lives are directly influenced by the urban performance of their surroundings. Urban performance refers to an urban area's ability to meet its residents' needs in terms of environmental, social, economic, and other aspects. For example, mobility refers to the efficiency and accessibility of transportation. Livability refers to the overall quality and satisfaction of life experienced by inhabitants. However, assessing urban performance, especially those involving subjective perceptions, is time-consuming and costly. Traditional methods requires trained researchers to conduct field audits, questionnaires, surveys, or interviews. Is there an effective approach to assessing and quantifying various urban performance measures? Moreover, can we achieve this through consideration of the residents' subjective perception so that we can answer questions like which part of the city feels more comfortable or is more convenient to live in? In this paper, we propose a solution using point of interest data, or POIs, as the semantic representation of urban functions. If we want to measure a specific urban performance measure, the spatial distribution of different kinds of POIs can tell us the major function of that urban area, providing us with a basis to analyze these performance measures. For example, the places where it's closer to the bus stops and subway stations exhibit higher mobility, and the places where laundry shops and shopping centers are more convenient. In our research, we collected 416,000 POIs in Shanghai, including 130 classes, such as office buildings, pharmacy, amusement parks, etc. We further categorized these classes into 12 categories, facilitating visual encoding assignments in our VIS system and reducing the participants' evaluation workload, which will be discussed later. Next, I will introduce how we quantify the POI's semantic contribution to different urban performance measures. We first construct corpora for each POI class and performance measures. The corpora consists of two components, definition and context. The definition for both POIs and performance measures are retrieved from WordNet synsets. We curate the meaning of the class names and measure names and extract the associated definition for these sentences. As for the context, for POIs, we collect the user comments from location-based social media and select the comments that can describe the POI's functionality. For performance measures, we collect internet search results, including blogs, white papers, travel websites, and related studies as initial documents. We split these documents into sentences and select all of those mentioning the performance measures and their surrounding sentences within a context window of 2. To measure the semantic textual similarity, we utilize a pre-trained language model and produce text embeddings and calculate the semantic textual similarity using the cosine distance of their embeddings. This similarity serves as a basis for analyzing urban performance for various measures. Next, I will introduce the generation of density maps for performance measures. The generation of these maps involves kernel density estimation, or KDE. So it is a process for generating a continuous surface from discrete sample points based on their density using kernels. However, plain KDE has two shortages, making it unsuitable for this task. First, it only reflects the distribution in terms of quantity, but fails to neither capture their impact on urban performance nor the semantic differences among different POIs. Second, the number of POIs differs largely from class to class. The impact of POIs with small numbers can be obscured by those with large numbers when using the same kernel value. Therefore, we propose semantic adaptive KDE as a modification of the plain KDE method, taking into account the POI's influential areas and their semantic contribution in the context of urban performance. First, the influential area. The influential area can be defined as the region within which the presence of POI attracts residents' visits and affects its surroundings and urban functions, controlling the bandwidth of the kernels. It varies depending on the POI's local density. For example, the influential area of an airport may govern half of a city, while the influential area of stadiums or police stations may only govern a neighborhood. To characterize this, we use traffic analysis zones as the basic spatial unit for analyzing the POI's local density. We calculate the POI's relative abundance and assign larger influential areas for POIs with higher abundance values. Second, the semantic contribution. It controls the kernel weight. The POI's contribution to the performance measure can be either positive or negative. For example, the presence of factories reduces the level of comfort in their influential areas, necessitating a negative weight. The semantic contribution coefficient beta here is calculated based on the rankings of similarity, where the first 3 quarters of classes are assigned positive weights. Finally, we normalize these class-level maps and apply the weighted average to generate heat maps for the performance measure. Such operation can keep the influence of POIs with varying quantities and highlight the spatial differences as shown in the picture. The combination of a SAKDE and weight in our method allows us to accurately reflect the influential area of POIs and their semantic contribution to the map. To facilitate interactive exploration of urban performance, we integrated our approach into a visual analytics system and identified 4 design goals. First, we leverage regional analysis. We leverage a circle-based selector and let users specify the focus range. Second, cross-measure analysis, allowing users to analyze the correlation and make comparisons among multiple performance measures. Third, explainability, enabling users to understand the factors that contribute to the final results. Lastly, interactive performance, allowing users to interact with our system responsively and make quick adjustments. So now I will further introduce our system with 2 cases, starting with enhancing house rental decisions. We start by setting our desired focus range. In this case, a few minutes of walking. Then we inspect the semantic map for livability. Using the circle selector, we can see the measure scores of each location, as well as the POI density, the relevance to the measure, and the diversity of POIs. Users can also check the distribution of a specific POI category. Now we've already added 2 circles for comparison on the right. We can add an extra circle here near Shanghai Stadium. We select other measures to compare, and we can then sort these measures with different sorting criteria. So from the results, we can see that among the 3 selected circles, Middle Huaihai Road might be the best option of the 3, for it had the highest average measure scores. We can zoom in and further check the POI details within the circle range. Next, in the second case, we use our system to identify areas where transportation bottlenecks hindered economic growth. We change the map to mobility. We can see, okay, we now first change our map to mobility. We can see that the mobility is highest in the central region, with hotspots occurring in almost every district. For economic vitality, we now change it to that map. Distribution follows a different pattern with more concentrated center areas. We now use our filters to curate areas with and we can find an area near Oriental Sports Center. Located in a rapid developing central business district, Qiantan, transportation in this area is primarily concentrated around the hub, making the nearby areas difficult to access and having fewer options. Okay, as for the evaluation of our system and method, we first assess to what extent our approach aligns with human perception in terms of the POI semantic contribution. We recruited 76 participants and let them rank the 12 POI categories according to their relevance to different measures, and computed the comparison correlation score between the model-generated similarity and the human judgment. Results indicate that our approach is feasible, and the strategy of building corpora with context and definition sentences further enhanced this correlation. We also evaluated the accuracy of our maps using reference data. We use objective data, house price, as the reference for economic vitality, and calculated the difference between the house price and all 8 semantic maps. The results illustrate the effectiveness of our pipeline, and since we can see that economic vitality is the most similar to the house price map, and it is the highest among all the methods. In summary, our paper focused on subjective urban performance analysis using POI data as the semantic representation of urban functions, and designed an easy-to-use visual analytics system for urban performance exploration. In the future, we could use large language models to better model the relationship between POIs and performance measures and interpret user intents. We could also consider transit time or road network topology to perform better distance quantification, or combining more diverse data modalities to generate more accurate and informative semantic maps. That's all for my presentation. Our project now is publicly available online, and we welcome you to visit it and have it a try. Thank you for listening, and I'm ready to take questions.
And thanks very much, Jingtong. It's quite interesting work.
Thanks.
And indeed, I have questions about this. How to you this understand this sense map. So did you try to? No, to my understanding now, it's only you only use the POI data, right? Do you consider about merging other like geographic information together with this POI data, and is your system can scalable to do that?
Okay, so I think first for the data source, yes, we currently use the point of interest data, and actually we use point of interest data and the user comments. So we combine their comments, the textual information, and the POS spatial location. We combine the information and use our a novel kind of new improved SKDE method to generate a heat map. So during this method, as for this, your second part of the question, the scalability, in our test case, I think we have like 400,000 point of interest data, and the results can be generated in a few seconds. So I think the scalability is not bottlenecked by the number of point of interest data. It's decided by the final resolution we want. So if we want a very high resolution heat map, like so we need to calculate lots of pixels, that will take lots of time. But for heat maps, I think we don't need very high precision resolution. So I think it can still scale to larger data scales, I think.
Okay, thank you.
Yeah,
And
thanks for the
probably there
question.
will be further questions in the Discord. I see our SVA is typing, so we don't have time waiting there, so you can check later.
Okay,
Probably there
so
are some questions.
I'll switch
Okay.
online. Thank you.
Okay, thank you. And let's come to our the next speaker, still Yutian Zhang. And his second talk is about CS-lens towards better deploying charging stations via visual analytics, a coupled network perspective. Let's welcome him again. You can open your voice. And now you are muted. Okay.
Okay, let's get started. I'm here again. I'm Yutian Zhang from Szabo University, and I'm here to introduce our work, CS-lens, towards better deploying charging station via visual analytics, a coupled network perspective. It is also a joint work by Szabo University and Shanghai Tech University. The number of vehicles has been increasing across the world, and as important infrastructures, charging stations are strong support for electric vehicles. Accordingly, improperly deploying charging stations leads to serious problems, such as poor charging experience, low utilization, and waste of investment. Generally, the average utilization around the world is still under expectations. A charging station may affect its surrounding traffic condition and power grid. The concept of coupled transportation and power network is proposed to better integrate a charging station with existing infrastructures. Nevertheless, decision-making process for charging station location problem under the coupled transportation and power network presents several challenges. It's required to analyze dynamic spatial temporal pattern revolution, predict post-deployment impacts, and integrate coupled networks in the same context. First of all, for charging station location problem, though there are many algorithms and models have been proposed, researchers tend to build models to generate results and overlook the analysis of the spatial temporal data, which result in insufficient evaluation. These limitations hinders the practical application of existing models. Second, visual analytics provides a promising tools to make full use of domain knowledge and big data analysis. Many representative visualization systems that have been supposed to facilitate location problem. To the best of our knowledge, there is only one work tries to analyze the potential impacts after the deployment, and the discussion is based on noise. On the contrary, in our work, it is more important to analyze the post-deployment impacts at the network level. For geospatial work net visualization, previous work mainly focused on visualize a single network, such as road network and power grid. In our work, novel visualized designs are required to assist the charging station deployment within the context of coupled networks. In our approach, we use 3 kinds of data to build up a model of coupled transportation and power network. The modeling of coupled transportation and power network involves 2 sub-problems: traffic assignment problem and optimal power flow. Traffic assignment problem aims to use origin-destinational data to generate traffic volume of each road, while the optimal power flow is used to determine the operational status of the power grid. We utilize the Groby Python's API to build and solve the model of the coupled networks. Some algorithms are also utilized to track the changes in the road network and the power grid. We also allow users to generate solutions and evaluate potential impacts after the deployment. Finally, a novel visual analytic system is proposed to assist the users in the decision-making process of charging station deployment. We conduct an observational study and got valuable feedback from 5 experts, which help us summarize the following system requirements, including information about comprehensive overview, spatial temporal variations, solution generation, and analysis of post-deployment impacts. Our system has 6 modules. The temporal overview is designed to identify traffic hotspots and track the evolution over time. We utilize a community discovery algorithm to divide the whole road network into distinct areas. Then we select top-ranked areas based on traffic volume as traffic hotspots. In the visual design, each orange rectangles encodes a traffic hotspot, and the red lines here connect the traffic hotspots, showcase the similarities. When users zoom in, each rectangle will turn to a glyph. The corresponding traffic hotspots are highlighted by blue lines, and the orange circles enclose the charging demand at different locations. The dual bars on the left of the glyph is used to analyze how much charging demand is actually served by existing charging stations. The charging station info offers an overview of existing charging stations. Users can sort charging stations by selected attributes. Besides, when users select the traffic hotspots in the temporal overview, the charging station inside the traffic hotspots will be highlighted. The map view provides an interactive map and insight into each charging station. A glyph on the map is used to display information about each charging station, including charging, demand, the service time. We utilize a purple wiring plot to analyze the voltage distribution at the location, which is useful to evaluate the operational states of the charging station. We allow users to zoom in, and an aerial chart will emerge at the center of each road, showcase the traffic volume of corresponding roads. When users select a charging station on the map, a pop-up window will appear to display how the charging demand of this charging station change over time. We utilize genetic algorithm to generate candidate solutions for charging station deployment. Users can adjust deployment target and the parameters of the model in the control panel. After clicking the Generate Solution button, the candidate solutions will be displayed in the result view. The impact view is designed to evaluate the post-deployment impacts in details. The line chart shows the temporal evolution of the charging demand across various solutions. Upon selecting a target solution, the corresponding curve will be highlighted, and the circles representing time points will transform into a dual bar. The height of these bars reflects how many rows of the road network or how many nodes of the power grid are affected, identifying the magnitude of the impacts. Moreover, users can select a specific time point to check more details. The spatial distribution of the impacts on the road network as well as the power grid at the corresponding time point will be demonstrated. And now we use a case study to show how CSLens works. First, the user found 2 traffic hotspots. According to the clear orange rectangles, you can see that those traffic hotspots also has high charging demand. When the user zoomed in, he found that the actual charging demand served by existing charging stations are less than expected, suggesting that there are still many potential charging demand. Next, the user moved to the charging station info and the map view to observe the charging station with more details. Judging from the red and orange bars, some charging stations are relatively small but have large charging demand, indicating that the service pressure of this charging station was very high. The purple violin plot shows the voltage distribution at different charging stations. Sometimes the voltage distribution will close to the lower limits. This indicates that deployment of charging station in this area is not reasonable enough, which may lead to imbalanced load on the power grid. Since there is also many potential charging demand, it may be useful to deploy new charging stations to balance the load of the power grid. Then the user generates candidate solutions for new charging station deployment. After waiting for a while, according to the predicted charging demand covered predicting the result view and line charts in the impact view, Plan 2 and Plan 3 generate better since they have a higher charging demand coverage. Plan 3 has the highest charging demand coverage. Consequently, the user click on the Plan 3 to examine the details. The glyph shows that change in traffic volume and voltage distribution, and the users filter out where the traffic volume increases. Some rows of an anterior rows turns red. The arterial rows belongs to one of the commuting routes in the city and is always congested. According to a new newspaper, well, you can see that these roads have consequently ranked the top 10 most congested roads for 2 years. Accordingly, though Plan 3 has more charging demand, it may increase the traffic volume of an arterial road, potentially leads to more traffic congestion. So we also received some valuable feedbacks from the domain experts. Our system supports the decision-making process for charging station location problem and offers a new perspective to related research. It also shows great scalability and user-friendliness. In terms of our limitations, our model of the coupled network is based on some basic assumptions and many factors. Due to computational complexity, it is difficult for CSLens to handle citywide road network. Looking ahead, we plan to consider more factors and reduce the computational complexity of the coupled network. We'll also propose new visual designs to demonstrate the coupled network more comprehensively. So that's all for our paper, and welcome refer to our paper for more details. Thank you.
Yeah, thanks very much, Yutian. And because due to the use more time than the limitation, so probably now we skip the question answering part. But you can also have to keep an eye on the Discord. So probably there will be some questions there. Okay, thank you again.
Thank you. Thank you.
Okay, so let's come to welcome our last speaker, Steven, and his talk is simple sets, capturing categorical point patterns with simple shapes. Let's welcome.
Yeah, thank you for the introduction. I'm excited to present simple sets, which is joint work with Wouter Meulemans and Bettina Speckman. It's a new type of visualization for categorical point data. So that's data like this. You have points on a map, and each point has a single category associated with it. Here's an example showing mills in the Netherlands, and each mill has a different type. And what we want to do is we want to create a visualization that helps the user in understanding the data distribution and perform tasks on the data. And one natural way of doing that is adding shapes to the map that connects points of the same category. So for example, shapes like this. And we will call these shapes patterns. And we measure the quality of a visualization according to several criteria. First of all, we want the visualization to have low cognitive load. So this shape, for example, has lower cognitive load than this shape. We also want to have a strong continuation between points that belong to the same category. So yeah, this shape provides strong continuation. It's a convex enclosing shape. You can also connect points with, for example, a line to provide continuation. We want little obfuscation of the underlying map. The line scores well on that, but the shape like this doesn't. And we want little distortion of point position and density. So this is a good example, and this is a bad example. So there's an inherent trade-off between these criteria. You could just visualize the points themselves. Then you have no obfuscation and no distortion, but you also have no continuation. And once you start adding shapes, you will inevitably add distortion and obfuscation. There are several existing techniques for visualizing this data, but they generally perform badly on cognitive load. There's line sets. They draw a curve through points of the same category. There are bubble-like visualizations, such as F2 bubbles. But both of these visualizations are quite complex, and can be intersections between the shapes. You can also have bubbles, multiple bubbles per category. Then either they cover a lot of the map or they do not connect much. And there's cluster sets, and the main issue here is that there is a lot of density distortion and obfuscation of the map. We present simple sets. This is a visualization that uses simple shapes that cover a little of the underlying map. And we designed it so that it scores well on cognitive load and it has little obfuscation, but we trade in some continuation in order to achieve that. We construct simple sets by first partitioning the points into patterns, then dilating them, and lastly, rendering them. So in particular, we resolve overlap between patterns. The patterns we use in our visualization are islands and banks. Islands are convex hulls of data points, and banks are polylines through data points. And the patterns in our visualization should be at the right scale. They should be regular, and they should not overlap other patterns too much. We capture scale with cover radius. That's the maximum distance within the pattern to a data point. So if we have an island like this, then this is a point inside the island that has a large distance to a data point. And you can also think of it as placing disks at the data points inside the pattern, and then the radius disk you need in order to cover the entire pattern, that is the cover radius. It also has a relation to the Voronoi diagram. For a bank, the cover radius reduces to the maximum edge length over 2. As I said, patterns should be regular, and what I mean with that is that it shouldn't have clear sub-patterns. So this pattern, for example, you can split into 2 smaller ones, and we want to avoid this. Lastly, we forbid patterns that have points that lie too far within the pattern, and we discourage overlap of patterns in general. So the partitioning algorithm, the idea is we use a greedy bottom-up approach, and intuitively you can think of it as placing disks at the points and growing these disks slowly. Initially, we have a partition that just consists of the points, and then every time the partition grows, 2 patterns are merged. And always the patterns that are in the current partition are completely covered by disks. We use discrete event simulation. An example event here is you have a bank and you have a point, and these then merge into an island. The result of the algorithm is a hierarchy of partitions. And at time t, all patterns have cover radius at most t. The patterns are pairwise disjoint, so they are not allowed to intersect. And we encourage regularity and discourage intersection by adding delays to the events in the event simulation. After we have partitioned the patterns, we dilate them, which is straightforward, and then we resolve overlap, which is a bit less straightforward. So after dilation, we have patterns like this. One way you could resolve overlap is by using some Voronoi approach, but here the result isn't so nice because we have a new type of curve in our drawing, namely parabolic arcs. And also the points can lie very close to the boundary of the shape, which is not nice because it makes it difficult to see what pattern a point is part of. You could also stack shapes and then avoid points lower in the stacking order by using some kind of geodesic hull. But with this approach, the shapes may be modified quite far away from the point of overlap. What we do instead is we also stack shapes, but we use circular cutouts to expose the points lower in the stacking order. And the problem with the geodesic hull approach becomes clearer in this example, where you see really the blue pattern is modified far from the point of overlap, which is not nice. And with our approach, the blue pattern has more similarity to the original pattern before modification. As I said, we stack shapes, and we have to determine what shape do we stack on top of what. We have 3 rules. First of all, we want to avoid modifying shapes if possible. We want to avoid modifying a circular arc if possible. We prefer modifying a line segment because it's easier to complete. For a similar reason, we want to avoid covering a circular arc. We compute preferences, stacking preferences pairwise, and then we create a drawing such that the preferences are satisfied. All the stacking is local, so you can get a drawing like this, and in that way we are more flexible than standard stacking drawings. We performed a quantitative evaluation in which we compared simple sets to cluster sets and VPF star 14. Those are 2 visualizations that also use multiple shapes per category. And the main conclusion is that simple sets occludes less than these other 2 visualizations and that its shapes are simpler. An interesting direction for future work is to adapt simple sets so that it can handle multiple categories per point. And there are several design and algorithmic questions that need to be answered before we have an automated solution. Furthermore, in general, for set visualizations, they struggle with handling large differences in point density. So that's an interesting direction for future work as well. You can try simple sets yourself on this webpage. We also implemented simple sets in Cartocrow, our algorithmic thematic mapping framework. And I was going to demo this at VIS, but unfortunately the demos got cancelled. So I hope we can do that some other time. Thank you.
Thank you very much, Stephen, and it's quite interesting work. I have a question about this. I indeed have 2 questions. So first one is that how did you decide that the different layers of who is on the top or who is on the bottom? And second question is that your approach looks like you will lose some make some the data set more disconnected. They are clusters, but you separate it into several parts. So will this reduce the cognition of some big cluster, or have you tested that? Yeah, so these are 2 of my questions.
Okay, yeah, so the stacking, we use these rules, and they're in in priority from left to right. So we first check if we can. We look at the 2 ways of stacking, and then we check is one stacking, does that cause less modification, or does it prevent modification completely? And then we prefer that way of stacking. And if we can't decide based on this first rule, then we check the second rule and then the third rule. I hope that answers your first question.
Yeah.
And then your second question, yeah, you're right. So our visualization uses more shapes and more disconnected shapes than other visualizations like cluster sets. And we rely more on color to match shapes that are not connected. And this is just a trade-off. We haven't done a user study, but in our visualization, we think we have a lower cognitive load and less obfuscation, and we trade on continuation in that aspect. But it would be interesting to do a user study and see the effects on the tasks, like if users perform tasks, if they perform better with disconnected shapes or with connected shapes.
Yes, I understand it's definitely the trade-off. Let's say we want to make it with less visual clutter but lose some continuity. Yeah, but I think it's an interesting method to explore again. Okay.
Thank you.
So thank you very much, Stephen. And also now I think we are really on time. It's good. And thanks very much for all the speakers and also the audience. And thanks that there are many questions already in the Discord. And I see some of our speakers already answer there. And I encourage you to also log in to the Discord and to see whether there are some questions that our SB will provide to you there. Okay, so let's wrap up this session, and we have quite many interesting talks here today. So I believe that the geographic space and the simulation and also this algorithm and the vast application will have more impact continuously because we have a lot of geographic data in the future. Okay, so thanks all, and that's all for our session. Okay. And also thanks for our student volunteer, Yishao, and she works behind. Okay, thanks you. Let's enjoy the VIS later. Okay, thank you.